And we are now recording. Let me go to current slide. And before we get into the actual physical science, let me go over the just a few announcements. I think I've probably told you before that last year, our volleyball team had the very best record they've ever had in school history. More wins than ever. And they got the same coaches and maybe half the same team and some new recruits. I'm hoping they're, doing quite as well this year. I don't know yet. But this evening, they do have a match at Bevel State up in Fayette, Alabama, wherever that is. It's supposed to be at 6 o'clock. However, the woman in my morning class said she would have had to leave early because she was, because they're leaving for the match. And I thought, they weren't supposed to leave till 2:30. But, it was an email that I got from her, so I didn't ask her. They may have moved up the start time. This weekend, Friday and Saturday, they are playing in the LaGrange, Georgia College Tournament over in LaGrange, Georgia. They don't have times for it yet, but if you happen to be driving by LaGrange, stop in and root the team on to victories. Okay? And then I'll give you the rest of those next year. Many of our people here who are participating in the College Bowl or College Scholars Bowl are probably also at PTK or whatever induction's going on now. But the Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. Okay, so Mr. Matthew West is the coach. His office is just down the half flight of stairs here, in between room 259 and 261. His office is in between those two rooms. It doesn't have a number on it, but it's right in between those two. So, are you participating in College Scholars Bowl, Ian? Okay, good group, isn't it? And from what I can gather, a lot of fun. Yeah, okay. The special exhibit that's going on in our library on the Birmingham campus will be ending, I think it's next Monday, okay? So please try to get over and see it. If not today, tomorrow, or Monday, is the Darkness of the Life, Alabama Holocaust Survivors through Photography and Art. And it will be ending September 23rd, which I think is Monday. So it should be quite impressive. Okay. And the NASA's Community College Aerospace Scholars Program is recruiting, is accepting applications through October 16th. I've got all the a lot of the information here. You can go to any of these websites and get more information and application process. Everything you need to know is there. If not, I can get you in touch with someone who can tell you the rest of the information. All right. Any questions on anything so far? All right. I'm getting tired of carrying around this stack of papers. So, folks, please, let's get the labs and tests done. Now, so far, I've received 4 research papers. I'm going to have to carry those because those don't get returned to you. But the first lab, there's 1, 2, 3 people haven't turned it in. And we actually have an inductee here. Okay. Patrick's here. A few others coming, or do you know? Don't know. Okay. There were some others at the event, right? From this class. Yeah. Okay. All righty. So please, 2 people have been attending regularly but haven't turned in the first lab. 1 hasn't been attending regularly, but he's got the first lab. Hopefully he'll get it done soon. First test. 1, 2 people who have been attending fairly regularly haven't done it. This guy who hasn't been here has even done the first test. So please get caught up on your first test. Lab 2, 1, 2, 3, 3 regular attendees, 1 that's not been. He's got it though, so he's working on it. Test 2, 1, 2, 3. He's turned in test 2. So only 2 people have done test 2. Not the same 2 people, by the way. Lab 3, that's the moon lab. I hope y'all are working on that. I hope those will start coming in soon. Test 3, 1, 2, 3, 4 people haven't turned that in. Lab 4, here's Tegan. There you are. Annie and Ethan. All right, come on. All right. So you get the picture anyway. I'm missing something from every piece of paper we've had so far, a lab or test missing from somebody. So please get these in. Yes?
Can I get the take-home test?
Yeah, I can. You wait till we have a sort of a break. Okay, good deal. Thank you. All right. My first moon lab's in. Good. All right. At break time, ask, okay? At break time, ask, okay? All right. So please, folks, I don't want to carry these around all term. Get your stuff in so I can get some of these papers back to you. All right. Any questions from what we've done so far? Just a little bit of review now of where we are. We are in Chapter 20. This is the last of what I consider the geology or earth science kind of part of the course. We had 3 chapters on astronomy, 4 chapters on the geology, earth science part. Then we'll have, which also is earth science, weather, and then oceanography. So we don't have that much left to go. We got a bit of time left, so we'll be moving on this. Now, last chapter, we did the lab, so if you weren't here for that, please get the lab also. And we had, as Tegan has mentioned, a take-home test. So please get your take-home test if you didn't get it earlier. All right. We're now in Chapter 20. Hopefully we'll finish Chapter 20 before 3:45 today. If we do, we'll have a lab today. If we don't, we'll just keep on trucking and may actually get started in the next chapter 23. There's not a huge rush, but I'd like to finish this chapter today, which I think we will be able to. We'll see. And then if we do the lab today, the test will be Tuesday on Chapter 20. And we'll get started on 23 at some point. So that's where we're sitting. Any questions? All right. Now, where we left off last time, we were talking about there's 3 types of weathering. You want to remember what they are. First one has 2 names. You can tell either one. Oh, 2 days too long. 3 types of weathering. First one had 2 possible names. Second, mechanical or physical. Okay, that was the first. What was the second? All right, it's right here in front of you, chemical weathering. The third type? We actually talked a little bit about it already. If it's not physical or chemical, it might be, think of another science. Physics is a science, chemistry is a science. Most people, biological weathering, that's the third type. You're not going to see much on the slides about that, maybe just a little bit. We're right in the middle of chemical weathering. 3 different ways of chemical weathering. There's more than that, but these are the 3 biggies. Oxidation, we talked about before. Reactions with oxygen tends to make a solid material weaker because oxygen breaks bonds. And the bonds don't hold as well together. That contributes to the weathering away of rocks, minerals, and that type of thing. The second of these, this is where we're starting today, is carbonation. Now, really don't care for this term because what they say is reactions with carbonic acid. And what carbonic acid is, can I ask you what's in your glass? Okay, and or something like that too?
Just ice.
Just ice, so kind of orange. Now, I'm guessing, does that have the little bubbles in it? Yeah. Okay, so what you're drinking is, in my guess, all right, look at this. All right, first take-home test has come in. And, Steve. Yeah! Yeah! Excuse me. Jordan's here. Okay. Took a lot to get that out. You know, I do have one more announcement I forgot about. I really wish more people were here because some of the people I think would be most interested in it are not here yet, but maybe they're not coming today. This is not school related, not probably even school sanctioned, though it doesn't have to be, but I just wanted to let you know about it. Has anyone heard of a strike happening tomorrow? Okay. You know anything about it? It's what? Oh, okay, right, okay. He's talking about the national strike. Okay, yeah, General Motors has a strike going on. There is another strike going on, basically worldwide. It's a school strike. Now, it's mostly high school students, but a gal in Sweden sort of got some of this stuff started. Okay? This is Maya, right? Okay. I brought my own today. Okay, there's Maya. Okay. A high school student in Sweden pretty much got this started, well, probably a year or more ago. It's on the environment. Okay, it's a strike for the environment. And a lot of high schools are participating, even some in the Birmingham area, and they will be gathering at, I think it's somewhere near Lynn Park tomorrow morning at 11 o'clock. And they're very concerned about the environment because our environment is not doing well. Global warming, this kind of stuff. There's a lot of sort of negative stuff going on in the environment. They're going to feel the brunt of it more than I will. I don't have that many years left. They've got their whole lifetime ahead of them. They're really concerned. So just wanted to let you know that would be, I hope you know where Lynn Park is in Birmingham. That's near downtown, fairly close to the courthouse and those kind of buildings. And that will be tomorrow morning at 11, if any of you are interested. I'm going to try to go myself. My wife is going to try to take off lunch tomorrow and go, so we're going to try to be there to support the high school students. One sort of reason we're a little fired up about it, y'all wouldn't know this, but we used to have a horticulture program here on this campus. And the instructor for that, the last instructor we had before they shut the program down, was Mr. Trey Tarrant. I worked with him quite a bit and kind of was a friend. We kept in touch. He has a daughter named Stella. And the voice and the picture we've seen of the Birmingham area student who's been talking the most about this is a student named Stella Tarrant. Now, how many Stella Tarrants are going to be in the area? I think it's that one. So we sort of want to go to support her, and I'm sure he'll be there too, and probably his wife. But I think his wife is a teacher in high school, so she may not be able to go. But anyway, they will be there. And if nothing else, it should be an educational experience. So it's not something that I'm saying lightly. It probably will be something you could learn something about too. So, wanted to get that said before I forgot about it. Okay, carbonation, what they're calling reactions with carbonic acid. The reason I asked if you had the bubblies in there, most of the time the bubbles in there are carbon. dissolved in water. And guess what that forms? Carbonic acid. Okay? You're drinking carbonic acid. Okay? It's very weak carbonic acid. What you got in yours? What's that? Okay, so it's not carbonated. So he's the only one with that. So just like every carbonated drink, sometimes it's phosphoric acid, most of the time it's carbonic acid. That's why it's not particularly great on your teeth, and especially if you have things like tensor ulcers or something like that, not great on those either. People with ulcers probably can't drink carbonated drinks too well. It's not a very strong acid, but it is an acid. And guess where we have carbon dioxide? And guess where we have water? In the atmosphere. So most rain, by the way, is slightly acidic. Naturally, slightly acidic, because it's got carbonic acid in it. Now, every time you have a lightning strike, some of that nitrogen, which makes up close to 78-80% of the air is nitrogen. Every time lightning strikes, some of that nitrogen gets split and becomes a nitric acid, which when it combines with water, nitric oxide, when it combines with water, it becomes a type of a nitric acid, which is a much stronger acid. Okay? Any sulfur dioxide in the air, when it combines with water, it forms sulfuric acid or sulfurous acid, one of those acids. Let's see. I don't think if there are any others. Probably are some others too. So rather than carbonation, I consider the more general term acidification. That's what's doing the damage, the acid. Doesn't matter whether it's carbonic acid, sulfuric acid, nitric acid, or what kind of acid, it's acidification. And it's just different compounds dissolved in water, which is in the air every time it rains. These easily dissolve limestone. Now let's get back to the sulfur. I mentioned where the nitrogen comes from. That's from the air. Lightning strikes, that can get slightly acidic. How about the sulfur? How does sulfur get into the air? Say again? Fires with what? You're right, just like anything that's burning is going to put a little bit. Some things are a lot worse than others. Say again? Volcanoes, oh, you're right. Plenty of sulfur comes out of them. They don't happen that regularly. What else is a big sulfur producer? Fossil fuels. Okay? Specifically, coal. Coal has high sulfur content. Most of it does. Especially your anthracitic coal, the cheaper coal. Unfortunately, most of the coal that they mine here in Alabama. Okay? And there's a lot of mining of coal in Alabama. Has been in the past. The bituminous coal from out in Wyoming and places, that's a little bit lower in sulfur, but it still has plenty of sulfur in it. Okay? But we still do a lot of mining of anthracitic coal. Where does it go? We don't burn much of that here in the U.S. because of the Clean Air Act, is the requirement. So we sell it to third world countries, and they burn it, and it messes up their atmosphere. But of course, their atmosphere has nothing to do with ours, does it? Heck, we all breathe the same air, okay? So yeah, just because we sell it across the border, it makes its way back to us. So, and not just coal, any fossil fuel, or most fossil fuels, gasoline, diesel fuel, all contain sulfur, okay? The one that has the least would probably be natural gas. That is a fossil fuel, but it probably has less sulfur in it than the others. That's why they brag on it being a cleaner burn than the others, but it's still. Now, they mentioned limestone. Sure. I think I mentioned earlier when we were talking about physical weathering, sandblasting the limestone buildings and things like this to get that crud off. What is that crud? The crud is because the slight acid in the rainfall dissolves away at the limestone, okay, and leaves debris there. So that's the second kind, carbonation. I prefer acidification. Now, what's highly involved with this? These things are dissolved in water. Any acid you are going to run into is going to be dissolved in water. Okay? What is it that makes an acid an acid? Does anyone know that? That's a little more chemistry than we've hit so far. Anyone know from high school?
Where it lies in the pH scale.
Say again.
Where it lies in the pH scale.
Okay. Now,
It has to be like greater than 7.
okay. Now, when you said pH scale, what does that stand for? Do you know? Okay. It's not exactly this, but you can think of this. Percent hydrogen. pH. It's not really percent, but it's close enough. Okay. The H though is for hydrogen. It's how much hydrogen. The hydrogen ion, that's the acid producer. So H2SO4, sulfuric acid. HCl, hydrochloric acid. HFl, fluoric acid, hydrochloric acid. HNO3, nitric acid. Every acid starts with an H. Dissolved hydrogen in solution, that's what eats away at everything. Okay? Now, what makes a base? That's the high end of the pH scale. Acids are the low end of the pH scale because it's a negative logarithm. So that's why it's sort of backwards on the thing. The more hydrogen you have, the lower your pH is. What makes a high pH? What is the ion that makes a high pH? Not the hydrogen ion, but the hydroxyl ion. Sodium hydroxide, calcium hydroxide, aluminum hydroxide, magnesium hydroxide, potassium hydroxide. Any of your hydroxides make your base. That's the opposite of acidity. Okay? What happens when an acid, oh, and by the way, limestone is a very good base. Very good base. That's what we use to neutralize the acidity in soils. We spread limestone to neutralize that. Okay? Why? Because you have a lot of calcium hydroxide, calcium carbonate, other things in there that neutralizes the acid. Well, what is it neutralizes the acid? The acid is the H. The base is the OH. And guess what HOH is? HOH. Water. H2O. Yeah. And that's what. So actually, where the H comes from is the water. When it combines with the carbon dioxide, the H comes from the water. Okay? And that's what is the acid form. All right, so that's carbonation. I think there's a slide that goes with this, a couple of them. Now, you've probably seen cuts like this in our area. This could be a little bit bigger scale than what we would have. Some of the road cuts on I-65 going north, some of the hills you go through that cut through, they will look a little bit like this. Why? Most of that is limestone. Most of it, not all of it. Okay? And where water has seeped into the limestone, acidified water with carbonic acid, hydrochloric acid, well, not too much hydrochloric, nitric acid, sulfuric acid, whatever acids are there, have eaten away at the weaker parts of the limestone and leaving the cracks, the crevices, and actually caves. It's hard to see in this picture, but they mention in the book you can pick out a few caves in there where the acid rain has eaten away at the limestone. This is a stream where the water, probably acidified water, has been cutting through, eating away Now, I can't tell if that's limestone now, but there's suggestion in the book is that it is. They say limestone. This is figure 20.6a and b. Says limestone caves develop when slightly acidic groundwater dissolves the limestone along the joints and bedding planes, which they don't describe very well, carrying away rock components in solution. Carbonation, acidification, that's one of the chemical reactions. This stream, the one on the right there, has carried away less resistant rock components, forming a cave under the ledge. And here's what they're talking about, that part underneath the ledge here. This is more resistant rock here, less resistant rock here. The water is eating away at that, forming a cave up under there. Okay? That's an example of chemical weathering. Slightly acidic conditions, mostly in water, will eat away at rock materials. Breaking down, remember when we talked about sedimentary rocks? What were the two stages of sedimentary rock formation? Called lithification. One was compaction, and the other was cementation. The cementation, that's what gets eaten away by the acidic water. Okay? But when the cementing agents are gone, the fragments leave. Okay? They get washed away. So this is the reverse of lithification, acidification. Okay. Now, the third type of chemical weathering, talk about water thing, hydration. These are actually reactions with water. Acidification is dissolved in water. Oxidation occurs with water as a catalyst, but this is actually reactions with water itself. Water is probably the most universal solvent that we have. Lots of things dissolve in water. What else is in your drinks? Probably sugars, not yours, it's just ice, okay? But sugars, okay? Perhaps some salts, maybe some minerals. Things are dissolved in there because water is a great dissolver, a solvent, okay? So reactions with water includes dissolving in water and combining with water. Now, what makes water such a powerful solvent? Well, it's that very, very akin to what we were just talking about. When you get hydrogen and hydroxyl, they combine together, but the two hydrogens are always on one end of a water molecule and the bare oxygen on the other end. Because it's trying to form a little tetrahedron with its electron pairs. It has 4 pairs of electrons. 2 pair with each of the hydrogen, and 2 pair are left just with oxygen, attached to the oxygen only. Okay? The 2 with the hydrogen tend to be positive because the hydrogen is positive. Oxygen hogs the electrons, leaving hydrogen, a proton, exposed. Makes it slightly positive. The negative end, where the 2 electrons are on the oxygen, that becomes a negative end. So water is a polar molecule. It has a positive side and a negative side. And because of that, it tends to break up other polar molecules, like sugars, salts, and lots of things like this. It will eat away at those, making it a great solvent, a dissolver. And things tend to combine with water. There are some clays that actually, when water touches the clays, they swell because the clays trap the water in between layers of clay particles. Now, you've seen the downside of that, I bet. If you've ever been near a clayey soil in really hot, dry part of summer like we've had now, what do you see in the ground there? ever seen those? Especially clay soils, okay? Little cracks will form. That's because the water gets desiccated away and the clay particles now have space between them and they form these cracks. Are any of you ever traveled or been much down in the Black Belt area of Alabama? It's around Selma, those areas? You have? Okay. Have you ever been out in fields in a dry weather there? Probably not. No. They say the clays, Selma chalks, make some of the most reactive clays around. And when those dry out, I've heard people say you can stick your whole arm down the cracks formed in those clays. Rather than the little surface cracks you see on most of the clays around here, you can actually stick your arm down in those cracks and get it all the way down. It's a very reactive, very intensive clay in its reaction with water. Okay, so when they say combining with water as a, and dissolving, well, guess what? When you combine with water and they swell up like this, then they slake off really easily because they just float away. Have you all followed any of the activities on the West Coast? Hydrologic, meteorological activity out there. They tend to be drier on the West Coast. There you got the whole Pacific Ocean there, and yet there's a lot of drought there. But they will have forest fires. Y'all followed that a couple of years ago, right? The major wildfires because things got so dry. And sometimes right after a wildfire, the next spring, when they get a lot of rain, what happens to some of those mountain mansions built up on the hills? They what? Mudslides, exactly. Okay? Let me get. Oh, man. It's our reach here, right? Okay. The mudslides. Why the mudslides? Because they have a lot of those swelling clays out there. And when the clays swell, big building on top of it, it just goes sliding down the hill. Okay? And that's a very major problem out there. There's actually a little of that here in Birmingham. Any of you are familiar with, I can't think what it's called, Eastwood Festival area? There's a Home Depot there, Edge Theater. Y'all know what I'm talking about? Oh, you know where it is, yeah. We live sort of out that way. That's where we do a lot of shopping there. There's a big hill there right above Home Depot. And if you ever notice when you drive up to Home Depot, look at the side of that hill, you'll see pipes coming out of it. Okay? And the reason is, you know what I'm talking about? Okay. That's because there's a lot of swelling soils there. Back shortly after we moved to Birmingham, I think it was, we had a lot of rain one spring, and some of those apartments that have been built way up high, nice views and stuff like this, those buildings, they didn't slide down the hill, but they started having lots of foundation problems because of that swelling clay. And then when they dry out, they get big cracks, and that's not safe. So that's another way, hydration, reactions with water. Okay? Pretty major. Again, chemical reactions. Physical or mechanical reaction, that's just the physical grinding, breakup, whatever. But even those, remember, wedging was caused by water freezing and breaking away rock. So water's involved with a lot of this. But here we're talking about the chemical nature of water. Okay? Hydration, strictly water. Mostly dissolution. Now, sadly enough, section 20.3, to me, the most important section in the book, is one of the shortest sections in the book. Sad, sad, sad. Soils. Anyone know a good definition of soils? Right there. Okay. Mixtures of unconsolidated. Now, what does that mean? Consolidated would mean joined together. Unconsolidated would mean loose. Okay. Unconsolidated, weathered earth materials. In other words, rock. Okay. Rock that has been weathered away, either physically, chemically, biologically. Notice we skip right over biological weathering. That's why we hit it a little bit in the physical side. But weathered earth materials, pieces of former rock. We call them soil particles. Okay? There's three classes of them. We'll get to that in a little bit. And humus. Anyone know what that is? It's not the Middle Eastern stuff you dip your pita in. That's hummus. This is humus. Here's the definition. Altered, which is a strange word. Decay resistant, which is strange. Plant material. Now, here's the other. It doesn't have to be plant material, but most of it is. Animal material could be there too. Most animals come from plants too, so ultimately gets to be that. What do we mean by that? Altered, decay-resistant plant material. If I were to ask you to describe a really good soil, okay, really rich, good soil, how would you start describing it? How do you think it would look or seem? Okay, you said black, right? You think of the dark soils as being rich soils. What you see there in the dark soils is humus. Altered, decay-resistant plant material. That stuff that's coated the soil particles. And you're right, it's in the black belt because there's lots of sites on those clays for the humus to attach. Okay? That's why they call it the black belt. The actual minerals there are almost whitish in color. If you don't see them, you see the humus attached to them. And they don't have to have a lot, but you have some. Okay? In reality, that humus really isn't all that nutritious. There are some nutrients in there. Granted, some. But most of what humus does for you is improve your water holding capacity. And what do plants need? Water. Okay? Water helps dissolve the minerals that are there, and the plants can use the minerals better. Okay? So yeah, it helps make it richer, but it's not because the humus is all that rich, it's because it improves the water holding capacity. Now, what kind of soil is worst about holding water? What would you say? Do you have any experience in your yard? Say again? Okay, to be a dry soil, that's hard. What soils tend to be drier more than others? Okay, lighter colored. Let me add this. Sandy soils. Why? Because, okay, we're going to get to it in a minute. Hang on to the thought. Let's go on to this one. Weathered materials. Up here, remember weathered earth materials? Weathered materials includes quartz sand. When you said whitish, light color, that's quartzy sand. Clay minerals, metal oxides, salts. Okay. Before we go there, I'm going to jump to this slide too, this side up. Now, we're going to get back to this in a minute. A soil containing varying amounts of sand, silt, and clay, mixed with an abundance of humus. Now, that's defined alone. Here I have what I'm looking for. Sand, silt, and clay. What's the difference between sand, silt, and clay? What makes the sand, the silt, or clay a clay? It's not what makes up the chemical composition at all. Most sands tend to be quartzy and tend to be light colored, but not all. There are dark colored sands that are made out of weathered basalt. I'll do dark colored sands, okay? There are some beaches, I think in California, that are very dark colored beaches, okay? They're not the pretty white beaches we have down in Florida and Gulf Shores. In fact, as you go on around the Gulf, the beaches get uglier and uglier. Texas and Louisiana beaches are not very pretty at all, okay? Our Florida and Gulf Shores beaches, those are really nice. The Mississippi beaches aren't that great, okay? We think anyway. So, sand, silt, and clay is not what makes up the material. It's the particle size. That's what does. A sand is a certain size. Okay? I only have one dime on me, but I have a penny also. They're about the same thickness. They're each about 1 millimeter thick. So two of those together would be 2 millimeters. That would be the largest dimension you'd ever have on a sand particle. Anything bigger than that is called gravel. Okay? Sand, that's what makes soil. Okay? The biggest you get would be 2 millimeters thick. Okay? They go down to some fraction of a millimeter. Let me jump down to the clay. The clay is the smallest particle size. I think I've told you this one before. Take that dime, slice it, if you could do this, into 1,000 equal slices. Can't even imagine that. You wouldn't even be able to see the slices by the time you got them that thin. You could look through them and not know they're there. Two of those together would be the largest clay particles you have. Those are called 2 microns. That is incredibly tiny. There's not a microscope, an optical microscope, that you can see a clay particle. They're too small. Electron microscopes, you can make out an image of a clay particle. That's about it. In fact, we saw some in our book, or, well, no, that was something else. Okay? That's what a clay particle is. Up to 2, and the rest of them are smaller than that. Okay? 2 microns. Silt is something in between. Okay? So here's how I like to, it's just a rule of thumb, you might say. If you have sand in the soil, if you rub it between your fingers, if you feel grittiness, that's sand. If it feels more like flour, that's probably silt. And the clays are too small, you wouldn't be able to feel them anyway. They would be just literally dust, and that's all. Okay, so let's go back here. Weather materials include quartz sand. It doesn't have to be quartz. It can be any sand particles. Okay. Clay minerals, that's the small stuff. Okay. And other things. Now, the reason they sort of mention the same. Silts are probably the lowest amount, are actually silts. You have more sands and or more clays. Silts is the smaller part. Well, let's get back to your water holding capacity. Your sands, because they're the largest particle size, then they have the largest pore size. The largest space between the particles. Because large particles tend to have a lot of space around. Okay? Now, large pore size means water just runs right through. Runs right through. There's nothing there to keep the water in place. So those tend to be your dry soils. When you said light-colored, sandy soils. Okay? What does humus do? Humus fills some of those pore sizes, and humus absorbs water really, really easily. That black stuff around in the soil is a good water absorber. Okay? Now, clay is also a very good water absorber. There's a difference, though. Once clay absorbs the water, it hangs on to it for all it's worth. It doesn't want to give it up. Well, why do you want the soil to hold on to water? So those little plant roots can get in there and get the water they need. Clays hang on to the water, and the plant roots compete and can't get the water out of clays, whereas humus gives it up easily. So that's why you add humus to a sandy soil, you improve the water holding capacity, because it holds it and then gives it up easily to the plant, but it holds it in place. But those clay minerals that tend to hang on to water too tight mix humus with them, and now they give up the water more easily because the humus is present. So humus will improve your water holding capacity of your, and not just water holding capacity, water giving up capacity too, so the plant roots don't be as hard. Okay? So that's why the humus is really, really important. That's why those dark soils are rich soils. They grow plants well because the plants can get the water easily. Not because they're any richer soil necessarily. Okay? Now, let's go back to this. Weathered materials include the quartzy sand, the clay minerals, metal oxides. I think I mentioned to you before, what's the famous soil in Georgia, you would say? If you had the name, what soil do you think of when you think of Georgia? Almost a phrase. Well, what kind of soil do you think of in Alabama? Think of most soils out in the field, what do they look like? Say again?
Clay.
And what color is clay? Red. That's what I was trying to get at. Georgia red clay. I'm 15 years old before I knew that was one word. It was one word. Okay. It was the clays, though, are basically a dull white. They're not red. What you see that's red is the iron oxide, the metal oxide, attaching itself to the edges of the clay. Now remember, the clays are so small you can't see them with a microscope. So the oxides are even smaller. And they just attach to the edge, and that clay looks red. It really looks red. What you're seeing is iron oxide. Most of what's there is a white clay. Once you chemically treat that and get the red oxides away, then you have a white paste. And literally most of it is that. The oxides are just coating the surfaces. Now the salts, these could be any kind of salt, not just table salt, not just NaCl, that's not very useful to plants. But potassium chloride, great fertilizer salt. Calcium sulfate, great fertilizer salt. Calcium phosphate, all these are salts that are also found in the weathered materials, okay? Because they were there when the rocks were formed, so when they break away, they're there again, okay? And some of them are nutritious for the plant, and some of them are not. Now, they mention one type of soil here. They're really biased, is what they are. This author was from, I think, from Arizona. That's West Coast, right? Yeah, Arizona State University, okay? The ideal soil, what he's saying is true, is a soil that contains varying amounts of sand, silt, and clay. Now, why is that? Like I said, the sand particles have big particles, so they have big pore spaces. Not because water runs straight through. But mix in with that varying amounts of silt, which take up some of those pore spaces and now slow the water flow. And mix in with that some of the clays, which even slow it down even more. They do tend to hang on to it. But here's the thing that clays, and by the way, humus has. Clays and humus have lots of sites. That's a strange way to say it. Sites along their edges and even on the flat portions that are nutrient holding sites. They grab things. Some of these salts, they'll grab and keep in the soil profile so when the plant roots come along, they can strip them off. Okay? They call that, you don't need to know this term, CEC, cation exchange capacity. The cations are the nutrients. These sites have places where those are. Humus is good for high cation exchange capacity, and so are the clays. So you need clays mixed in there, even though they hang on to water too tightly, they have sites for the minerals to hang on to. You need humus, an abundance of humus, so it also contributes to water capacity and nutrient capacity. Now, they say a loam is also known as a topsoil. Out west it is, okay? Here in Alabama, your topsoil may be just inches thick. What you see when you see those clay hills, a lot of times that's subsoil. You've lost all your topsoil, or a large part of it. So that's not fair to say a loam is also known as topsoil. In some areas of the country, maybe it is. Okay? Now, what makes a loam so good? You have lots of cation exchange capacity with the clay and the humus. You have good water holding capacity with a good mix of sand, silt, and clay. That's a great thing to have as a topsoil. If you had it, you're in good shape. Now, I spent some time in Nebraska. I did my doctoral work out there. I crammed a 3-year program into 5, so I was there for about 5 years. And out there, they measure the topsoil not in inches, but in feet. Okay? And there's a reason for that, and we'll get to that a little bit later. It's so rich, okay, that they can just bring a bulldozer in and move topsoil from here to there, level the field and stuff, and still have feet of topsoil. We can't do that. If you bring a bulldozer in, you're into the subsoil right away. When we went to build our house over in Georgia, and they were digging out the foundation, the guy almost tore up his bulldozer just trying to break through that clay. It was hard as a rock. I think he almost got so, he was a redheaded, high-tempered guy, and he was fighting that so hard, I think it hurt his health. He never seemed to be as healthy again after that. It was a hot day. It was miserable. The subsoil is what we see quite often. That's the less fertile soil that's beneath the topsoil, if you have topsoil. Okay, it contains more rocks. Have you ever dug much in Birmingham or Bessemer or any of these areas? You're going to hit rocks at some time. More rocks, and sometimes more mineral accumulations. But usually they're not very available minerals because they're contained in the rocks. And the big news is it contains less humus. Now, one of the sad things about the soils we have around here, it's a good thing, but it's a bad thing. We have high temperatures, nice, and we have high amounts of moisture, nice. The high temperature and high moisture eats away at your mineral content. If the high moisture dissolves it and washes it out, the high temperatures make it react more quickly. The higher the temperature, the more chemical reaction you have going on. Here's another rule of thumb. 40 degrees Fahrenheit, pretty chilly weather, right? For every 10 degrees that you go up past 40 degrees, you double the rate of your chemical activity. So if you're losing a little bit of mineral content, because at 40 degrees, you're going to double it when you get to 50. You're going to double that when you get to 60. You're going to double that when you get to 70. And guess what? A lot of areas of the country, most of the winter, they're below 40. Way below 40. Hardly any chemical decomposition of soils at all. Down here, you may have a few days or maybe a couple of weeks that are consistently below 40. Not many. Even in the dead of winter, you're going to get days in the 40s, 50s. It might get cold at night, but it gets back warm in the day. You're going to have mineral decomposition going on all the time. That's why our soils are less fertile. We can't hang on to that humus. The humus decomposes at higher temperatures. Okay? And large moisture content. That's all on soils, folks. I'm sorry. Okay. Now we get into 20.4, which is probably one of the most important sections in here. Because up till now the things we've been talking about tend to make soils a little bit better or make maybe rocks worse because they're tearing them down. But, there's some good benefit. This is just about totally bad. Erosion. 3 types of erosion. Well, the four, I guess you'd say, they talk about. One, they classify as mass movement. Who answered the question about when they get the rains in California? Okay, what did you say that was? Mudslides. Mass movement of soil down the hill. And mountain states, they may call that an avalanche. Mass movement of rock and soil down the mountainside. Okay? That could also be icy stuff too. That's what we mean mass movement. Okay? Big quantities moving down. Mostly mudslides, avalanche, landslides, whatever you want to call them. What is that caused by? Gravity pulling stuff downhill. Don't have mass movement uphill, that doesn't happen. As you may have heard, most things move downhill, okay? You won't get into what things, okay? Erosion in general is caused directly by gravity. I want to say in general, not directly, because there's one type of erosion that really isn't. We'll get to that in a little bit. It's the least of the erosions, but it isn't caused by gravity. The rest of them are mass movement caused by gravity. The mudslides are always downhill, right? The landslides are always downhill. The avalanches are always downhill. Gravity is pulling them down. Okay? Now, one type of mass movement, only it's not very massive, is called soil creep. And again, we're talking about soils mostly here, but it could be anything too. Creep. Now, what does that connote to you? Very slow movement. Probably not noticeable movement. You're going to notice a mudslide. You're going to notice a landslide or an avalanche. Yeah, that's going to be pretty obvious. Creep is the slow movement of soil down a steep slope. You won't realize it's happening, but it is always happening. Gravity is pulling it downhill. Now here's, I think, sort of a made-up thing, but I have seen something similar to this. Okay? This tall, straight pine tree growing on the hill here. Oh, here's Lexi. Why did I take my glasses off? I can hardly see. Okay? But further down slope, that tree started growing, and it was growing straight, but because the soil is being pulled downhill by gravity, then the tree gets being bent. And I have seen trees, predominantly I think probably around Smith Lake or some of those areas where there's been movement down, and you'll see some trees that are really, really crooked at the base. Okay? And that's because the soil is pushing down. Okay? The tree is always trying to grow toward the sun, but when the base gets moved, then that gives the bend to it. All right, soil creep. Slow movement of soil down a steep slope. The more rapid movement, that's a landslide. Any slow to rapid downhill movement of materials. That would include mudslides or any other rapid movement down the hill. Mostly that you can see. The soil creep is so slow you won't see it. You see effects of it, but you usually don't see the actual movement. Now I can remember when I was in, I don't remember which grade it was, some early grade, reading about the farmers in France that are down in southern France near the French Alps, had some pretty rich soils there. And, you know, down south they grew pretty good things, plenty of moisture and stuff. But that in the old days, they literally would dig out soil from the bottom of the hill and take it back to the top of the hill because they knew every season, especially when they cultivated those fields on the hillside, they're going to have erosion going downhill. So they go and take soil and move it back uphill so that it can always happen. That's very labor intensive. We don't do that kind of stuff anymore, but that's how early farmers kept things. Somewhere under there is solid rock, okay? But the soil that's been formed, very thin on the slopes. It gets thicker as the slope decreases. Okay. So basically, mass movement is the big classification. Most mass movement is caused by gravity. And these are the two smaller classifications: soil creep, slope, landslide, more rapid. Something you could see. Now that's strictly caused by gravity. The most serious, I would say, if your house is falling down a hill, you might say the soil landslides, mudslides would be the most serious. But I think overall running water is the most important of the gravitational erosion process. Remember water? Water is involved with physical weathering, involved with chemical weathering, and involved with biological weathering. You can't have biological material without water. So it's involved in all three. So running water is going to combine these. Now, they call these the three-stream transport mechanisms. The first thing that water does, and we mentioned it before, it dissolves materials. Okay? Water is that great solvent. It will dissolve some of those cementing agents. It will dissolve the stuff that's holding the fabric of the soil together. It dissolves the material. Okay? It also suspends material. Now, what's the difference between a solution and a suspension? Does anyone know that? Remember that from high school science? A solution or a suspension? All right. Whatever you said the drink was that was in there, could you, if you held it up to light, could you see light come through it, you think? Not in the cup, but in the bottle. Huh? Maybe, maybe not. Okay. I'm thinking something like, well, let's do something like Sprite. You certainly can see through that. But is Sprite just water? No, it's got a lot of sugar in it, a whole lot of sugar in it most of the time, and it's got some other flavorings and stuff. That's a solution. Anything that's clear that you can see through, light will come through and stuff, that's going to be a solution. A suspension would be something more like milk. Milk is mostly water, but it has not things dissolved in it, but things suspended in it. Those things include fat particles, especially if it's not a non-fat milk. It includes calcium particles. It includes all sorts of things. You don't see through milk, okay? It's a suspension, okay? So water does both of those. It dissolves materials and comes out looking clean, but it really isn't. And it suspends material and carries the suspended materials away too. Now, beyond that, suspended materials are still very small. You don't see the individual materials. But when you have rapid moving water, you can actually carry along rolling, bouncing, and sliding things along with the water. Gravel, sand, silt, clay is all being carried with the water. Okay? Now, when it does go over the stream beds, especially gravel and sand, it's eating away at the spring bed. Because the water's moving rapidly, carrying that abrasive material with it, and it's making the stream bed dig up more. So the stream bed evolves over time. Now this author really likes this concept, because you're going to see it now, and you'll see it again at the end of the chapter when they talk about landforms. Okay? So he must count it pretty important. Okay? And by the way, running water, we're on page 512. And make sure I haven't skipped anything. There are some examples here, but it's slope, percentage grade, and that kind of stuff. It's just making up some problems for you to work on. I don't see that much substantive stuff to that. So, well, before we get to this, stream bed evolves over time. Here's you can tell there's just been a rainfall. And this is in some pretty hilly type area. Nice dense green foliage there, but guess what? That water coming down, what do you notice about it? It's not nice clear water, is it? It's got suspended materials in it. Maybe some rolling, bouncing, and sliding materials in it too, but definitely some suspended materials. Clays suspend really easily. Okay? Other things, even the silts will suspend. The sands, not so much. They'll be rolling, bouncing things, sliding down too. Okay, but there could be some suspended. And that's joining other water that's running downhill. And if that's running downhill, you know it's picking up more and more stuff as it goes, the faster it goes. Once it slows down, it starts dropping some of that stuff out. And we'll see the effects of that in a short while too. Whoa, okay, here's the stream development. This last slide here, that bullet there, should have been on the next slide. Stream development evolves over time. So here's the stream development. And like I said, this book loves this concept. A youthful landmass, okay? Something that's recently gotten there. Maybe it's been uplifted. When I say recent, within the last few thousand years, that's recent, okay, geologically, okay? What you have is steep gradients. Let's get a picture of them. Steep gradients, meaning a high slope, a large value slope. V-shaped valleys, okay? V-shaped valleys, mostly, okay? Without any floodplain. There's a little bit of floodplain maybe in there, but generally not. You have lots of boulders, rapids, that's where water runs really quickly, and waterfalls. Now, they don't show many waterfalls in that. But that's a youthful landscape. Now, do you remember one of the very first pictures in the chapter? And the rock was sort of yellow on the side. Remember what we said that was from? Yellowstone. Okay. Notice, remember that valley? I mean, almost perfectly V-shaped. The water running right down the vertex, and the sides went straight down. That's a youthful landscape. Okay, recently uplifted, steep gradient, very steep slopes there, and V-shaped valleys. No floodplains, just water running down. And we saw a huge, beautiful waterfall there, the upper Yellowstone River Falls. Okay, rapids and boulders. Now, a more mature landscape will be one where the stream gradient is smooth. It's not running downhill as fast, it's running sort of more gradually. It's still going downhill, of course it goes downhill, but it's a lot more gradual. The hills are more gradual. The hills have eroded, okay, smoothed out some, not the stark, deep, steep valleys. The rivers then tend to what they call meander, because it's a very slow gradient. Meander over the floodplain. And there are floodplains. See all this area in here, near the streams? When there's too much water, it fills in that. No place to fill in here, it just goes faster. But here it fills in, and it does go faster, but it has got a floodplain. Now, you've been maybe reading or hearing about that lately, too. Especially the Mississippi, okay? I can't remember where specifically it was. Somewhere in the Mississippi, they've had, which I can remember for sure. Seems like I can remember hearing they've had 3 500-year floods in the last 10 years. Okay. Whoa, okay. That's way more than they're supposed to have. In other words, places that were only supposed to flood once every 500 years or so, they've had 3 in the last 10 years. Hey, that's something's different about this picture. All right, now when we get very old age, we're talking about stream development. Later we'll talk about landform development. They use the same terms. Very low gradients, okay? Broad, gently sloping valleys when you have them at all, okay? and sluggish flow and more floods because you get more water in here. It's not going downhill because there's nothing much downhill. It's just filling in. Okay. Now there's other things that happen here, and there's a picture of one of these here, and I do want to point this out to you. Now these happen, remember, over long periods of time. You know what this is called here? It's called a bow lake. Okay? It's a lake here. It's not actually going anywhere. It's just sitting there. And it's a lake, but it's a bow lake. Where did that bow lake come from? Way back, this river probably went this way. But somewhere over time, somehow this filled in or this ate away more, and then it started flowing this way and left water here. That's called a bow lake. Okay? My wife's brother has a place. He lives in Alexandria, Louisiana, and he has a place in Natchitoches. Now, I can't spell Natchitoches. It doesn't spell anywhere like it sounds. Okay, it's a really strange spelling. It's Louisiana, remember? And they have their camp house, they call it, or something like that, on Cane River Lake. Cane River runs somewhere like this, but what used to be Cane River is a bow lake here. It got separated from the rest of it. Probably the river ate out a deeper channel here and left that high and dry. So they have a place on Cane River Lake, which is a bow lake. Now this is not quite a bow lake, but I did run into this. I think I may have told you about going over to, no, I doubt if I did that in the past. My wife had professional meetings in Lake Como, Italy. Nice area. And Lake Como is one big lake, but it's part of three big lakes. They're sort of like three fingers that do like this. This is Lake Como. These two are good active lakes. This is where the resort is, but it's a dead lake almost because it's not going anywhere. There's no outflow to it. It's just it's collecting water. These two have outflows. This one doesn't. So you really don't want to eat too many of the fish you catch here. That's a pretty stagnant lake. That's not quite the same thing as this, but it sort of is. This lake is no longer flowing water. It just is collecting water. But it once was a part of the river. And this happens on old age floodplains, stream development. Okay.
So then they can dry up too.
What's that?
So those bow lakes will dry up.
I can't hear you.
So they can dry up.
They can, but usually they don't. They're in areas that have. Here's the other thing. In places like this, they have. We'll talk about this in a couple chapters from now. High water tables and plenty of rainfall. So usually these are. The water table is right up near that. So they hardly ever dry up. They just don't cycle through water the way they ought to. So they get a little stagnant. But he still fishes in them, and they eat the fish, so I guess it's okay. All right. Oh, there's the picture again, isn't it? What kind is this? Old age, mature, or youthful? Youthful for sure. Look at those steep V-shaped valleys here. No U-shape in them at all, okay? The gradient is way rapid downhill, okay? Both in the river and down the hill. The gradients are huge there, okay? And like I said, this is Upper Yellowstone Canyon, waterfall. I believe that's the upper. They mentioned waterfalls here. There it is. The reason is highly resistant rock here. The rock down here eroded more quickly. This up here didn't, so it catches it, and then it falls over it. Now, you may find this hard to believe, but at one time, this was the waterfall. It was probably closer together, but you see it's eaten away. When water is moving that rapidly, it's wearing away rock. constantly. This is just wearing away more slowly than this did, but it's still wearing away. Like I said, the waterfall used to be up here, probably before that was up here and up here. It's just gradually, and it's going down. Probably a few centimeters a year or something like that, but it is wearing down. And moving back that way too. Moving water like that is going to eat away even the hardest of rocks, okay? Nothing here. There is a pretty good picture in your book, actually a couple that one I missed earlier. Let me hit this one now. This is on page 512, figure 20.8. Moving streams of water carried away dissolved materials. You can't see the dissolved materials, but I guarantee you they're in there. And sediments. Lots of sediments suspended in that water. You can tell by the color, okay, as they slowly erode the land. Bad, sad, okay? And then this one up here, this is the river usually stays in its channel, but during a flood, it spills over it onto the adjacent flatland called the floodplain. And you can almost make out, here is the river. It looks like it's here and here and bends there and there and there. And you can almost guess this probably used to be an old stream bed here. Not there anymore. Okay, maybe that was. Maybe, can't tell what that is. But you have high water tables, so you have lots of little lakes dotting around here. That's a very mature landscape. Almost flat, and the river meanders around, okay, just trying to find the easiest way downstream. At one time it may have been through here, but it found the easy way there, even though it's a little longer. Okay? Now, oh, and there's in your book, let's see which one this is. The waterfalls and rapids of the Yellowstone River. They don't say which waterfall this is. It's either upper or lower Yellowstone. Okay. So, that's stream development. Now we're jumping a little bit here. I think we are anyway. No, we're not. We're still in the same place. This is on page 514. What in the world is a delta? Not like the triangle, that is a delta, but that's not the one we're talking about here. What is a delta? It's a deposit of sediment at the mouth of a river or a stream. That's what a delta is. Well, guess what? That moving water, especially way out there, moving very fast, very rapidly, eating away at stuff, hauling stuff downstream. Then it goes through a more gradual stuff and starts dropping stuff out of solution. Out of suspension, okay, dropping it. And then when it finally gets down near the mouth of the river, it's almost flat. So now the water's moving very slowly. The slower the water moves, the less energy it has to carry stuff. So stuff falls out. When it falls out, it leaves sediment. So that's what builds up the deltas, okay? The stream flow dissipates, that means slows down, as you come close to the ocean, the lake, the whatever it's dumping into, Gulf of Mexico, whatever. Okay? The erosive and sediment carrying abilities are lost because it's slowed down so much, so it starts dropping those sediments out. Now, get my good old visual aid here. You probably can't see it from where you're sitting, but you can imagine it because you've seen it in a lot of maps. What is it that comes down this part of the country right here? The Mississippi River. Now, the Mississippi River is also fed by the Missouri River. And that system of those two rivers is one of the mightiest systems of rivers on the planet. The Nile, the Amazon, maybe the Ganges in India, couple over there that are pretty major, but none of them beat the Mississippi, Missouri by much. They may be a little bit, but not by much. Okay? Now, that starts, the Missouri especially starts up here in the Rocky Mountains. Maybe it's still not called Missouri there, but things that feed into it. You have areas up here that feed the Mississippi. The Ohio comes in here. The Tennessee comes in. There's just all these rivers coming in, building onto it, all of them bringing plenty of sediment, right? When they finally slow down, what is at the mouth of Mississippi? Yeah, it's a delta. What state is that? Louisiana. Now, I don't think it takes too much imagination. Can't you see that's Louisiana that sticks out into the Gulf like that? You know why? That's all the land, the soil, and the sediments that have come from all over the U.S. and sedimented out there. I bet you at one time this was a very smooth boundary here on the Gulf of Mexico. Louisiana hardly existed then. Louisiana, not the upper part of Louisiana, but the lower part, just about all deposited materials. Sediments, delta, that came out of upstream. Okay? That's where it originated, upstream, and settled out there. The stream flow dissipates into the ocean, the erosive and sediment carrying abilities are lost, and it drops. All that stuff has been carrying for miles and miles and miles out. Now here is an actual picture of, and this could easily be Louisiana. I don't think it mentions in the book what it is. I don't know if that picture's in our text anymore. No, they've got an aerial shot now. This is from an earlier edition. Okay? But it's easy to imagine all the soil you see here, one time miles and miles upstream, it's been carried down by the water. When the water slowed, it dropped it out. And it dropped it out in layers. Here is a natural bedrock here, okay? It did fall off into a basin here, but at one time the water went up to here, okay? And the soil filled in, layer on layers on layers on layers on layers, and built up, and soon you have land up here. Okay, that wasn't there before. This was all soil brought from miles and miles away and deposited here. Okay, all this has been deposited from somewhere way, way upstream. In fact, as far as you can see, it's almost flat as a flounder here because it's all been deposited. All of it, okay? Not just a little bit. The bedrock is somewhere way underneath all that. Way underneath all that. Those are all sediments. Those are good, rich soils too, okay? My wife's brother's family is from Louisiana, and boy, they've been farming some of that deep, deep topsoil for years. Good stuff. Really good stuff. Thank you, Canada. Thank you, Midwest, for sending all that down to Louisiana. Now, I don't know if you ever thought of glaciers causing erosion. Had you? They do. They do really big time too. It's just they're so incredibly slow. Really, really slow. Okay? What are glaciers? They're masses of ice on land that move under their own weight. What makes them move? Gravity. Gravity is the cause for all this, right? They're being pulled downhill by gravity. It's just that they're so massive, such thick, massive layers of stress, they move really, really slowly. Okay? They form from snow being accumulated and accumulated over a number of years, anywhere from 5 years. If you've had 5 years of consistently heavy snowfall, that can start a glacier. Or more likely, 3,500 years. Some of these glaciers have been in the process of being built up millennia. Okay? Two major classifications of glaciers. Now, this one is a little, the naming of it is very geocentric, you might say. The Alpine glaciers, guess how it got its name? First three letters. The Alps, okay? Because Europeans, they say, oh, these glaciers formed in the Alps. Well, no, they form anywhere there's high mountains. But because they were European, they named them the Alpine glaciers. They're also known, the more general name is valley glaciers. So these are formed at very high elevations. Now, at very high elevations, the air is much thinner and it's cold. The more you go up elevation, the cooler it gets. Okay? There may be several reasons for that, but it just happens. So therefore, it's very seldom will you rain at really high elevation. If you have precipitation, it's snow. So every time it precipitates, it's snow. And it doesn't melt that much, so you build up, accumulate more and more snow, and that's how you form the glaciers. Form at high elevations, and then, because of the weight of all that, it slowly moves downhill. Because they're in the mountains, and the mountains have slopes, and they move downhill. Because they're frozen, they move very, very slowly. Okay? They're also called valley glaciers. Let's see if we got a picture. Yeah, here's one. You can tell that there's a valley somewhere in there underneath here. You can see sides of it here, but this is filling the valley. A really deep, deep valley. Okay? That's a alpine if you're in Europe, or a valley glacier anywhere else. Okay? They flow through the valleys. Now, flow is a really generous term here. Creek would be more like it, except we hardly use that. They not meander. They just move so slowly, but they always move downhill. There's another kind of glacier. I don't think we have a picture of this. This is a continental glacier. They cover large areas of a continent. And these are always in the extremes. The extreme north, Greenland, lots of continental glaciers. Northern Canada, I'm sure has them. I'm just not familiar with them. Northern Alaska, I'm sure has them. We've been to one over in British Columbia. My wife's family went on vacation one year. We went up to Jasper in British Columbia. I believe that's in British Columbia. And we went to the Columbia ice fields, even further north than that. It's one big expanse of the glacier. It's a continental glacier. Ice field, they call it, because the whole field is covered with ice. But the really sad news was, we got to the place and we parked, and we started going. I was younger then, and started walking, and we finally found a stake in the ground, and someone had marked that's where the glacier was at. And the Europeans first discovered it. Of course, people who lived there knew about it for centuries probably. But when they first discovered it, someone drove a stake down in the ground, and that was what we call the tongue of the glacier, the very end of it, where it started melting and running off. We had to walk another probably mile and a half to find the tongue of the glacier. It had retreated that much in right at a century. Ooh, I mean, that's not good. We've also been to Glacier National Park in Montana. Beautiful, beautiful park. Now, sadly, the year we went, there were a lot of forest fires, not in the park, but somewhere near it, and there were smoke was in the air everywhere because of the wildfires down in lower elevations. But we did get to drive around the park and into the park quite a bit. And I think, I can't remember now, there's only like maybe 6 or 7 glaciers left in Glacier National Park. They're predicting, if things continue like they are, that within maybe 1 or 2 generations from now, there may only be 1 or 2 glaciers, or maybe no glaciers in Glacier National Park. way back when they named it, there were bunches of little glaciers, none of which are buried. It's not pleasant. Anyone remember a guy named Ernest Hemingway? Okay. Pretty famous writer. One of his, I think, fairly early novels was the Snows of Kilimanjaro. I've not read it. Have any of you? So you wrote that. But Kilimanjaro is an incredibly tall mountain in Kenya. Well, on the border of Kenya, maybe in Tanzania. Okay. I don't think that's all. See if I can find it here. Awfully close to the equator. Okay. Together. See if I can find it. Yep. I think I found it. Yeah, that's it. Kilimanjaro, just south of the equator. Right there. Mount Kilimanjaro. Okay? And his book was The Snows of Kilimanjaro. There were glaciers there. You go to Kenya today, you see a beautiful green mountain. There are no more snows. I'm sure in the wintertime, at really the highest elevation, you'll see some. But in general, not year round. It just doesn't happen. Oh, and there's no such thing as global warming. Well, we won't go into that. Okay, so the continental glaciers, like I said, Greenland is the big place for them. There is some in Canada. Alaska doesn't really have too many. It probably does up north, but Alaska has so many mountain ranges, those are mostly going to be valley glaciers there. But the other big place for them, Antarctica. Antarctica has a lot of mountains too, so it'll have some valley glaciers, but it has a lot of very flat areas, and those are just continental glaciers covering most of it, or at least it used to. Those are melting away at alarmingly high rates too, but there's so much there, they still got a ways to go. But those are the biggest continental glaciers. Greenland and Antarctica, but both places there are diminishing. So, how does glacier erode land? Well, there's three mechanisms. They like three, and they like mechanisms. The first of these is the front of the glacier. As the glacier advances, now most glaciers are retreating right now, but at one time they were advancing. Okay. As the ice is pushing forward. And they're still, in those valley glaciers, is pushing forward. It's just melting at the end and moving further back. But when they were advancing, they called what they did bulldozing. Because they're going downhill with a lot of, often slowly, but still a lot of force behind them, and they pile up soil in front of them, like a bulldozer. Okay? Break apart the soil, rocks, boulders and stuff, and pile it up in front of them. That's bulldozing. It forms deposits called moraines. And as long as they're advancing, they keep pushing these things down, building them up, okay? But at some point then, the glaciers start, the cycle ends and they start melting. And then sometimes these big piles of moraines, especially in a valley glacier, this big pile of rocks and soil and everything else, boulders, gravels, everything, they form a natural dam. And as the glaciers melt, the water fills them behind it. One of the most beautiful lakes we visited when we were in Canada, I can't remember where it was, it seems like it was near Jasper, was one called Moraine Lake, because those accumulations at the front of that glacier, the deposits that were left there was called the moraine. And we got out and walked. I mean, there were boulders the size of this building, and then smaller ones like house size and stuff like this. Just it looked like someone had just dumped them there, and the glacier had pushed them there for probably miles ahead of it. And then when it started retreating, it made a great dam, and then a beautiful, beautiful lake behind it. It was called Moraine Lake. Now, of those happened. I wasn't around to see it. I can't remember the name of it. But there was a place in the West, fairly close to where Salt Lake City is now, but a much bigger area. And, the Rocky Mountains are there, and there were glaciers during one of the ice ages that pushed down through and left a moraine there. It wasn't a very well-developed moraine, but it left behind it a lake that was bigger than the Great Lakes. I mean, it was enormous. I can't think now what the name of that lake was. But that haphazard moraine dam at the end of it started leaking. And then it started leaking rapidly, and then it washed out. And this lake that was the size, bigger than the Great Lakes, I mean, probably the size of several fairly small states here, back here, it was huge though. That started dumping and ran down the Snake River. And the Snake River does a lot of this, but it ran down so fast, it dug outside. And my wife and I were driving through this, and I said, Karen, why are the sides of this river vertical? Most rivers have angled sides. This is vertical sides. Why? What could have made that? Well, we traveled on, we kept seeing it every time we crossed the river, vertical side. I mean, you'd look down off the side of that, look straight down, and there'd be people in a kayak and stuff, and they looked like ants. I mean, it was that deep. But vertical sides all the way down. This isn't normal. What caused this? Finally, we got to one of the markers, and it gave the story. And that lake dump, that water was rushing down the river and basically dug out a vertical trench. It didn't have time to do this. It just straight through, because it ran for weeks, emptying that lake. And that's what dug the river so deep with vertical sides. It's just absolutely incredible. That moraine gave way, and those were the results. So that's one thing. Bulldozing, that's how it does erosion. Picking up rocks ahead of it, bulldozing on the head. Those are called moraines. They also, the glacier, sometimes, I mean, the depth you wouldn't believe. I mean, hundreds, if not thousands of feet deep. Okay, the ice is packed in there. It's packed so tight it's often blue ice. It's not white ice; it's blue. It's packed in there, and it's moving under an enormous amount of weight. And when it moves, it's on the bottom of that, moving across maybe rock. Whatever it's moving across is grinding it to death. And that's what produces powdery, silt-sized flour, rock flour. That's where most of our silts come from. Sands are gritty, clays are too small to be seen. That floury like silt, there's not that much of it, but that's mostly formed by the abrasion of the glaciers. Okay? Some of it's made its way down here somehow or another, but we don't have that much silt. And then the next way is plucking. Well, what that means, have any of you ever ice skated? Have any of you ever driven over? Oh, you have? Yeah. Okay.
Well,
ice skating, okay. Why is it now? When I ice skate, my ankles usually do this, so I'm not a very good example of it. But when people know what they're doing ice skating, how can they glide so easily? What happens? The blade. Okay, now you have to get a couple of physics terms right. Pressure. Pressure is force per unit area. Okay? Fortunately, I have a force of about, let me just round it off to around 210 to 15 pounds. That's my force. That's my weight. Now I'm standing on the floor here on pretty big feet, wide feet, stuff like this. So that whole weight is being applied to an area that's less than a square foot. So I would have a pressure of about 212 pounds, well, let's say 200 pounds per square foot, okay? Let's just say 200 pounds per square foot, that's the pressure. Now, if I were standing on a narrow little ice skate with a single blade like this, my area there is just a few square inches, maybe, right? So now I've got 200 pounds per square inch, okay? Whoa, that's a lot more pressure, okay? And what ice does, when you add pressure to it, it melts. So when you're skating along, you're melting the place where the pressure is the greatest, but then as soon as the pressure releases, it refreezes, okay? So when the glacier's skating along, so to speak, the glacier water that's underneath there, that it's pressing on and melting, okay? It melts and then it refreezes when the pressure gets a little less, but it's now all around the rock. So it freezes around the rock, and now they call that plucking. It freezes into the surrounding rock and pulls it along, and it acts like a plow, okay? A subsoiler that is digging into the thing. That's another form of glacier erosion. The bulldozing in front, the abrasion underneath, and then the plucking and freezing boulders and gravel and rock. So it's basically sandblasting the soil underneath, but at a very, very low rate. All right. Now, by the way, do y'all remember I think they called it the snowcopolis or something like that a few years ago? What was it, maybe February of one year, and they were calling for a light dusting of snow one morning, and it came down heavy, right in the middle of a busy, busy morning. And people tried to get out. We started closing businesses and schools. They tried to get out. The first people out, no problem, because they ran over that snow, and the snow just crunched under the wheels, melted as they ran over them, but then when the wheels wet, it froze back. Now it wasn't crunchy snow, it was ice. And the more cars that did it, the more it happened. And the thing is, the night before that happened, it was sub-freezing. So the ground was very cold, below freezing. So nothing melted and went into the soil. It melted and refroze. So after a few cars had run over that, you're on a skating rink, okay? And that's why, because the pressure melted the snow, refroze it to ice, and enough of those happened, and you were soon nobody could move anywhere. Okay? This is what the plucking does. It melts it, refreezes it, and carries it along, grinding everything underneath it. Right? Okay. We are right about page 516. We'll pick up and look at this figure right here. All right. Where we left off last time was on page 516. There is a pretty nice picture of a valley glacier. We saw one, but here's one in Mount Logan, Yukon Territory, which is in Canada. That's a pretty broad valley glacier, but it is a valley glacier. You can tell the end here looks like, to me, it's retreated quite a bit from where it probably once was, because there's, I bet you that was underneath the glacier at one point. Okay. Now, what we have here at the bottom, it shows kind of a maturish-like landform. We were talking about this before. Between early age and youthful and mature, okay? The valleys are a little bit V-shaped, not as sharp as we've seen on some. The mountains are a little more rounded, okay? Meaning it's not brand new landform, so it's not completely youthful. The ridges are kind of rounded, so this is in between youthful and mature, probably. Now that was before the glaciers came. Let's think of an ice age, not the movie, but an ice age that came and started filling this, okay? And it got very cold. All the precipitation was snow. It didn't melt. It piled up and piled up and piled up. And then rather than water going down the valleys, very slowly the glaciers were moving down the valleys, okay? Then after a while, it warmed up again and they started retreating. What did they leave behind? Where the glaciers came through these valleys here, they ate out using bulldozing, abrasion, and plucking, ate out the valleys. So rather than being a little bit V-shaped before, maybe a rounded V, now they were U-shaped valleys. These were U-shaped valleys. Wherever there was a valley before that was sort of V-ish shaped, now it's more U-shaped. And the rivers are still running down the base of those valleys, so that may erode even more. Now, some of the features you do have some waterfalls where this glacier didn't eat as deep because it wasn't as heavy and thick into this side, and then hit where this one was. You could easily have a waterfall there. It doesn't show it too clearly here, but it could. And they sometimes call that this is a rock step where probably it stopped when it was retreating, dropped a few more rocks off, and then went back again. This is a hanging valley here, which may form a waterfall. These rounded peaks you have now got eaten away by the glaciers, and just a few of the things. Don't worry about these terminologies, but you get what they call rock basin lakes here, probably from the bulldozed moraines that came ahead of the glaciers and made these rock basin lakes here. Where a glacier ate on one side of this smooth valley and another one ate on the other side, that left a ridge, and these ridges are called, the peaks are called horns, and the ridges are called, I don't know how to pronounce this, I think it's arêtes, okay? I'm not sure, but I believe that's what it's called. Where you have sort of an eaten out area like this, that's called the cirque, or something like that. And that could be a little lake or something up there that's running downhill. So these are a few of the unique kind of, and these are again rock basin lakes up here, maybe from the moraines that were left by the retreating glaciers. These are just a few of the landforms that are unique to a former glacier area. If you ever go to see any of these, you'll probably be able, if you take a back off view from them, you'll probably be able to detect and see, oh yeah, okay, I can see where that could have been a glacier that later retreated. Because we did have at least 4 major ice ages that they've been able to tell. Maybe some smaller ones in between. Hopefully we're not heading toward another one, but who knows. Now, I think that's it for glacier erosion. The last type of erosion is also probably the mildest form, unless it happens to be where you are, considerably less efficient than water or ice, is wind. And this wind is the one kind that is not caused by gravity. Okay? Wind is not caused by gravity, so I hated when they said all erosion is caused by gravity. No, wind is not. But it's the least of the important. There's 2 major processes, and if you can let your mind drift a little bit, these are not too far from what we saw with water erosion. Water erosion, first, I can't think of the word now, detached materials, and then transported. Well, the wind does the same thing, only its detachment we call abrasion. That's another term for it is natural sandblasting. Sandblasting is not natural, but if you have that. In other words, the wind's blowing with considerable force, usually in fairly constant direction, picking up sand or other materials and blowing it against the side of rock. And as it does that, it eats away at it. Okay? And that eating away is abrasion. It produces what they call ventifacts. A vent meaning air, wind, ventilation, that type of thing. These are artifacts caused by wind, ventifacts. Okay? Some of the more unique forms that you'll see sometimes are ventifacts. The shape can depend on the prevailing winds. Have any of you ever been out to the West Coast? I think San Francisco, LA. Okay. Did you notice? I've only driven through LA. I've never stopped and stayed there very long. The wind seemed like always hanging off the Pacific. That's called the prevailing wind. Okay. And San Francisco always blowing in. Oregon, Washington, always generally blowing in. In fact, our prevailing winds are mostly from the west to east. Mostly. Not always, but mostly. I haven't figured out what happened last night. My wife said, "Oh, that front came from Georgia." No, fronts don't usually come from Georgia. She said, "Yeah, Georgia was cooler than us yesterday, and we got it last night." Fronts don't usually come this way. We'll talk about that in the next chapter. But the prevailing winds, okay? And that often affects the shape. And we'll see it, in fact, maybe right now. Okay? If the prevailing winds are almost always coming, say, left or right on this rock, it's been eating away at that rock over and over. Now you get a rock that's shaped like this. At one time was fairly symmetric. Now it's more gradual on this side, steeper on that side, because prevailing winds have eaten away on it. Now, if by chance, for some reason, there was a persistent shift in the wind direction and it started eating away here, then it would go back to being a bit more symmetric. But most of the time that doesn't happen. Usually the prevailing wind stays that way. Now, they do show something funny here. The wind has picked up a rock and blown it into here. And that adds to the abrasion. It's not just the force of the wind, it's usually the sand or other particles being carried by the wind that start eating into that rock. Okay? So that's one form of erosion. That's the abrasion part. The deflation is then when it picks up that loose material, carries away, and hits the next rock with it. Okay? And therefore it starts eating away, sandblasting away at the next one. So the first part is the detachment or the abrasion. The second part is the transport. They call it deflation as it carries it and drops it somewhere else. The loose material is picked up, carried away by the wind. Then if it hits some other rock, it starts abrading that rock. Okay. Now, deposits that are formed from wind have two names. Most of the time near the ocean you think of dunes, but you can have it in other places. Low mounds or ridges of sand or other sediment that the wind has deposited. And of course near the ocean, the wind usually comes in off the water, most of the time, coming in off of that and dropping into dunes. And any wind coming this way will sometimes slow down and drop them. So that's the dunes, low mounds or ridges of sand or other sediment. But there's another deposit, it's a strange name, L-O-E-S-S, is pronounced lus, not lust, but lus, L-O-U-S-S it sounds like. It's fine dust deposited over a large area. Now, that can happen anywhere at any time, but there was one time in history it happened big time. Does anyone know when that might have been? If you...
The Great Depression.
Second?
The Great Depression.
Yeah, it was around that time. Let me back off a minute. Are any of you veterans of the Gulf War or any of the activities there? Well, they say in the Mideast, you have a lot of lusts around because there's those sandstorms that come in very frequently there, and they, lots of, in fact, I say most of the deposits in some areas there are lusts, okay? They're wind erosion, okay? But I think what you were talking about, it was about the time of the Great Depression. I think it preceded it a little bit. What we had done, and it was sort of unfortunate, when we were doing our westward expansion, growing into the country here, we happened to be settling our Midwest at a time of, and we didn't know this, at a time of unusually high rainfall. We didn't realize that it was unusually high. We thought it was normal, natural. So people moving west, the farmers looked at this great, huge prairie. Most of the trees were not there. It was a prairie, okay? Funny thing is, that grass, my goodness, those roots were deep and thick because that was all. By the way, I meant to say this about the glaciers. Let's back up for a moment here. Remember I said there were 4 major ice ages? In every one of those ice ages, the glaciers came down out of Canada and dug their way. In fact, some people suggest that the Great Lakes were dug by glaciers. Now, I don't know if that's true. If it was, those were some mighty big glaciers, or maybe were filled by glaciers. But what happened here, the glaciers, probably the continental glaciers, coming down out of Canada, ground their way along, taking up the topsoil from Canada, carrying it with it, came into the upper Midwest, and then finally stopped and started retreating. And as they retreated, they dropped all that nice, well-found ground topsoil into our Midwest. That's why the soils in Nebraska and Iowa, Indiana, and some of those Midwestern states, you measure the topsoil in feet. Some of the richest farming land in the world. Our Midwest. Why? Thank you, Canada. Thank you, glaciers, for scraping off their topsoil, bringing them down, and dropping it off for us to use. Okay? We appreciate it very much. Okay. So, what we did as we were moving west, and they saw this very rich topsoil, great farming, okay? But they had to dig through all those prairie grasses. Those prairie grasses, the root systems went down for feet. Well, there weren't many bricks out there. There weren't many rocks out there. So what they did, they built the houses from chunks of that sod. And they called those houses soddies, okay? They just dug up squares of that and built houses with them. Real thick walls. It was pretty cold in the wintertime. That gave great insulation. There's some of those old soddies there. I had a friend when I was in Nebraska invited me out to see her ranch out in the sand hills of Nebraska, and her mom lived in a soddy, a former soddy. It had been covered over. You couldn't tell it was a soddy, except the windowsills were that deep. Okay, that was a soddy. Okay, but anyway, so we came out and we started digging up all that prairie grass, making building houses with them, and then plowing the fields, planting corn, planting crops. Well, then that unusually high rainfall stopped. It went back to normal. And does anyone remember what that time was called? Now you had the plains, and the winds come whipping down the plains. If you're an Oklahoma fan, the musical, not the football team. Okay, winds came whipping down the plains. Now there was no more grass on top to hold the soil in place. The crops were failing because it was too dry. What do we call that time? The what? The Dust Bowl. Exactly. That wasn't a football game. It was that was a different football. That was the time I'm talking about. They said that lusts from the Midwest settled out in Philadelphia. They had sand, silt dropping out of the sky in Philadelphia because the winds were that strong and ugly, ugly time. We should never have done it, but we didn't know any better. Okay. Now remember I said what we saw with stream bed formation, we're going to see the same type of talk here about development of landscapes. This, by the way, that was wind erosion. We just hit it, okay? Before we go too much further, I was talking earlier, there's a myth, mistakes, and misunderstanding. To me, this one's pretty weak. You may have heard the phrase, as unchanging as the hills. Very poetic sounding. But guess what? The hills are always changing. So they're slow, but they are changing. The next page, page 518, is out of place, or the blurb called it is, Science and Society Acid Rain is mentioned here. And it gives several substances and their natural acidity. Hydrochloric acid is, the pH is almost 0, okay? That's as acid as you can get. Stomach acid is next closest, 1.6 to 1.8. My goodness, that's acid. Well, that's what your stomach does. Your stomach deteriorates everything you eat that you eat, breaks it into solution and sends it out to the body for your body to use. It's a very strong acid. And that's why when someone does have a disturbance in the stomach lining called an ulcer, those are incredibly painful because that stomach lining has to be some of the strongest material on earth to be able to withstand that kind of acid. When you have a break in it, boy, that's miserable. Lemon juice, 2.2 to 2.4. You like to suck on the lemon? Don't. Your dentist won't approve of that, okay? Vinegar, 2.4 to 3.4. Ooh, I like my vinegar too, okay? Carbonated soft drinks, 2.0 to 4.0. Didn't know you were drinking that much acid. No, that's a different kind of, never mind. Okay. Grapefruit, 3.0 to 3.2. Not quite as bad as lemon, but pretty close. Oranges, 3.2 to 3.6. I love my oranges too. Acid rain, 4.0 to 5.5. Natural rain, got down the list, 5.6 to 6.2. Big difference. Tomatoes, I had tomatoes for lunch. No, I didn't yesterday. Okay. 4.2 to 4.4. Potatoes, I didn't know they were that, but you're getting less acid all the time. 5.7, 5.8. Natural rainwater, 5.6, 6.2. Milk, still slightly acid, lactic acid, but not much, 6.3 to 6.7. Pure water, which you very seldom drink, 7 on the nose. What's that? Oh, I thought you were pointing at me. Okay. Oh, it is time, isn't it? Is that what you're saying? All right. Let's just finish this quickly, okay? But there's a nice blurb on acid rain that we were talking about earlier. Landforms, the Earth's surface features. You have the broad features that we talked about in the last chapter, the mountains, the plains, the plateaus. Then you have minor features, hills, valleys, canyons. So I wouldn't call the Grand Canyon very minor. Then, what are some generalizations about these? One is the rock structure. The mountains are the most resistant. The valleys, they weren't very resistant. Weathering and erosion, what kind, how much, what contributed. Stages of erosion, how far along are they in their erosion? All right. There's more here than I thought. Let me just, just 3 more slides. Okay. The rock structure determines the shape of the minor landforms, refers to the type of the rock. Is it igneous rock? That's going to be pretty resistant. Metamorphic rock, maybe even more resistant, especially to chemical weathering. Sedimentary, low. That's the least resistant to physical or chemical weathering. So, what type of rock? That will help determine some of the landform. The attitude of, hey, that rock has an attitude. No, this means where is it facing, that kind of stuff. The effect of the disturbance by faulting or folding. The faulting and folding can hasten erosion. Yeah, if you've had that, remember what they called the ladies, what do you do? Defoliation, where you had pressure differences. That from faulting, where you've had the breaks, where the break occurred, you're certainly going to hasten erosion there. Okay? The weathering and erosion process. Now this is a fairly important slide, so let me hit it, maybe not quite as fast. Influenced and controlled by such factors as climate and elevation. Climate, two features. Temperature, moisture. Okay? And as I was saying, here in warm, moist climates, chemical weathering is dominant. For every warm part, for every 10 degrees you go up, double your chemical activity. All right? Think about how many days of the year are we over 40 degrees. Our soils are weathering constantly. Okay? Also, the chemical weathering happens better in moisture. Acids are moist, everything happens faster in the presence of water. Okay? Where you've had this, the landforms are softer, rounded outlines. The Appalachians, look at those mountains. Most of them rounded. Go out west to the Rockies, jagged. Dry out there, not as much rainfall. Also maybe a little cooler. Here in the wet, moist southeast, very soft, rounded. Drier climates, mechanical weathering dominates. That's where wind is more important, okay? Sandblasting, okay? Here you have sharper, angular outlines are much more common because the chemical weathering has not eaten away at things as badly. So the big news here, the two features of climate, moisture, and temperature, we have them both. So we have high degrees of weathering here. That's why our topsoils are not measured in feet, they're measured maybe in millimeters. No, very, very little. And here's the stage of development. That's what I was talking about before. Do these words look familiar? Now we're talking about landforms, same process. Youthful, the weathering and erosion effects are just beginning. Okay? The mountains have steep peaks, narrow, steep valleys. Okay? In a more mature landform, the original structure is worn down, the rounded peaks, gentler slopes. Okay? In the old age, characterized by nearly flat rolling plains, and there are, this is a term I never see anywhere else except in this book, peneplains, the nearly flat surfaces, where the plains are just almost totally flat. Whereas, every now and then, you'll have a monadnock, another really strange word I've never seen anywhere else. These are hills of resistant rock. Now, they say resistant rock, sometimes they can be resistant soil as well. When we built our house, like I mentioned, clay, that clay is so hard, it acts like rock, but it was more resistant. Around there, it's valleys, that hill is clay. Now, rejuvenation. Remember we've said just by every chapter, things happen, things rebuild. Landforms are uplifted, erosion begins again, it starts the process. Everything's a cycle. It begins again and again. That's the last slide. Let's just hit one more thing here. John Wesley Powell is mentioned here, a really attractive looking dude. He was one of the, they say, a romantic figure in the 19th century. I don't get it, but, 19th century U.S. geology. So maybe that's how he's so romantic. Okay, I don't know what they meant by that. But anyway, he was the mind behind a lot of what we understand now of geology. John Wesley Powell. This cannot be your topic. This cannot be your source for your material. If you want to write on him or anything that's mentioned here, you certainly can do so. There's several other names listed: Grove, Carl, Gilbert, Clarence E. Dutton, W.H. Holmes. There's many things mentioned. The Grand Canyon, how was it formed? Colorado River, there's just tons of things in here you could choose as a paper topic. Now, I'll say this again, say it every chapter. Nothing replaces reading the chapter. The summary is awfully short here, so don't count on that. But it does have several italicized words. The key terms, very few in this chapter, fewest I think of about any chapter. Applying the concepts, though, there are 45 questions. That may be a few fewer than normal, but not many. Those are all multiple choice. If you know those, you have a really good shot at understanding the material. Questions for thought, 18. That's about normal, maybe one or two more than normal. For further analysis, 3, maybe a little less than normal. Invitation to inquiry, frost wedging. That might be something you might look at. And then parallel exercises, as always. These are kind of made up. Now, we've just finished Chapter 20. We're not going to do Chapter 21, Geologic Time. I wish now we were, but your books don't have them. And then, but anything in this you can write on, like Edward Seuss, okay? You can go through the chapter. Neither are we doing 22, Atmosphere of the Earth. Sort of wish we were doing that one. It makes more sense. So I would say it might be a good idea to at least scan through Chapter 22, because the next one we do is 23, and we're going to have to stop and go back and define a few things from 22, so that if you scan that, you'll probably be in better shape for 23. All right, that's where we'll pick up next time. So let me pass out the labs. Okay. Goodness, this stack is way too thick. Oh, and by the way, I've got to call roll again, so don't let me forget to do that. All right. All right. Copy.
Are we doing this together?
Pardon me?
Are they working on this by themselves or together?
Some of us, not the whole class, but the people will be doing a bit more like last time. Okay. Take one, pass 3, 5, 1. One, pass 2, sideways. Okay. Take one, pass 2, sideways. And 1 and 1. Okay, did I give too many to anybody? Anyone wind up with 2 or more? Okay. All right. I'm going to turn back on the recorder here. What's that? I know, but somehow I turned it back on. I didn't mean to. I must have just hit the keyboard. I'm going to. All right. Now, can I get you to, Patrick, maybe turn on the other light? This lab is probably one of the more important ones to be sure you read, okay? Because the first few questions you answer are going to come right out of the reading here, okay? Now, they talk first about several types of maps. Most of you are familiar with road maps, but we're not going to deal with those. You used some last time for latitude and longitude. What we're dealing with this time is topographic maps. These are maps that somehow show elevation. Hills, valleys, whatever. Okay? There are also geologic maps that are kind of like topographic, but they don't show the actual topography. So read that, especially the definition of contour lines. These are on topographic maps. You're going to be using these. So read and understand this concept of contour lines. Okay? Another name for a contour line is an isocline. Iso, that prefix means same. Cline means elevation. Lines of equal elevation. So if you have these on the map, then you can show where things are getting taller or lower. The trouble is, you can't tell which is which unless you look at the numbers or pay attention to what's around anyway, they have some samples here at the bottom of isocyclines or contour lines. Okay? So read this. The second page, 346. A lot of those points there that you see, 9 points and some sub-points, a lot of that stuff is going to show up in some of the questions. So read that carefully. Make sure you understand. Materials, we don't play with this size lumps of soft clay. We're not going to have any clear plastic shoe boxes or any of this other stuff. But I'll explain what you're going to do. Okay? You're going to read the front part and then answer the questions on the results. This all comes from the reading. Okay? Page 347 and 348. 4 questions there, and then at the end you'll answer the 5th question. Those come from your reading, so read your readings. Then, for those of you who have computers or your phones, go to, and I don't know if this website is still active. One time it was, then it wasn't. I don't know if it is now anymore or not. But you can Google or search somehow for Devil's Tower National Monument, Wyoming. Topographic or relief map, okay? They sometimes call it relief map, sometimes a topographic map. Those are the key words that you need to get somehow in your search. And if you can find a topographic map of Devil's Tower, then answer these 5 questions. Now, if you don't have access for that, get with someone who does. That's why it's a lab, and you have to work together in a group. So that gives you 5 more questions. We're up to 10. And that's all, folks. So we have to come up with 15 more points worth of material. Okay? And here is how we're going to do that. Remember the map from before? I said it was a topographic map, a topo map. This is the state of Alabama. Okay? And remember, most of you live on pages 30 and 31. Okay? So I'm going to use that as a sample here and show you what I'm talking about here. If anyone's familiar with Birmingham Decimal, here's how we sit. Now, the yellow part has nothing to do with topography. The red lines, those are streets. Don't pay any attention to those. But what you pay attention to are these little gray lines. Notice here the gray lines are close together. Here they're really, if you look at that, it says Sand Mountain. No wonder they're close together. Because the contour lines, when they're close together, that means you have a steep slope. When they're far apart, that means you have relatively flat. Those very little slope. So you look for the gray lines, not the red lines, not anything else, the gray lines down here. Here's close together. Oh, where's that? Double Oak Mountain, where not, okay? The gray lines are really, really close together down there. So I'm just giving you some areas where they have very close together. And there's plenty more of them here. But then you come out here, and those little gray lines are way far apart. That's near Short Creek, Sylvan Springs. There, what does that mean? Very flat. The elevation is not changing very much at all. Okay? There could be hills, monognots, or something like that, but they're generally pretty flat. Okay? So what do you do for the rest of it's actually going to be 16 points worth. I want you to find 8 different pages, like 2021. That's a page, a pair of pages. Now, not all of these will work well, I'll tell you that. Like 34, 35, something like that. Find pairs of pages like that, and then find places where the contour lines are very close together. Find something on there that indicates what that is, like I just did for what here, Double Oak Mountain, Sand Mountain, or where they're very far apart, Sylvan Springs, Short Creek. find something in the general area that shows where they're far apart. So what I want you to do is make a table or a chair if you are better. No, I'm just kidding. A table. And let me end this. This will take a little bit of while to open, but not too. Oh, there it opened really quickly. Okay. And here's what your table should be. Okay, now this looks like it's landscape. I would do it letter, but basically put page numbers. Okay, page numbers, right? 24, 25. I'm not saying that's one of them. It's two pages that open up side by side, okay? I think ours is 30, 31 or something like that. So page numbers, whatever you do, and you're going to do 8 of those, 8 pairs of page numbers, okay? Then, features with close lines. These are contour lines. The lines are close together. Find a feature on those 2 pages where the lines are close together. Now, folks, let me tell you this. Down here in South Alabama, you may find something. You can't hardly find a contour line. Why? The whole thing is flat. Okay, so you're going to be sticking mostly up here in the, probably above what they call the fall line. Okay, but look and see. You determine that. Okay.
So features are cities or.
Well, no, it would be something like I just said, sand mountain, something hill, something. It could be a valley. That would have steep slopes, close thing. So it could be a valley, something like that. Give it a geologic thing. Now, place where it's an open area, there may not be a name, so then pick a town or pick a feature, like a mine or something like that. So features with close lines, name the feature on those 2 pages. Okay? So for every page that you do, a feature with close lines. And then, what does this mean? And I've just told you several times. What does this indicate? I can't write, so, okay. What does that indicate? And it'll be the same thing for every one. Okay? Then, features, and this could be towns or locations, something like that. Features with widely spaced lines. In fact, you may not even be able to find the lines. I can't write. Goodness gracious, this is awful. Widely spaced lines. These are contour lines, by the way. Okay? And what does that mean? And I think I've told you that a couple of times. Okay? And write that down for everyone. It's going to be the same thing. Okay? Any questions on that? What's that? Flatter. Steep. Exactly. That's what it's going to mean every time. Yeah. What does that mean? Yeah. Does everybody understand that? Okay. So, 3 parts. Reading the lab, answering those questions, looking up, finding Devil's Tower Monument, whatever that is, with a contour map of it, and see if you can figure out those answers, and then finding, what does say, 8 pages with this information, 8 pairs of pages, like this one is 32, 33, or whatever, okay? So, I had it like 24, 25, whatever. You want me to leave this up, or y'all got it? Leave it up? Okay. That's the only topographic map. So I'd say I'd say some of you need to be doing this, wait and do the other later, and then swap the things around. Okay? I'd say somebody use the maps. And y'all can do it in teams. That's why I said it's sort of together, sort of separate, whatever. Okay. How about the recording? Does anyone think you're going to have lots of questions? Or? Okay, great. Thank you. All right. All right. Remember next time. 2 hours of class on weather and climate, chapter 23. Oh, no. We may have 4 hours of that. Okay? And then 30 minutes of test on chapter 20 that we just did. All right.
So no lab.
What's that?
No lab.
I don't think we'll finish chapter 23 because the lab for 23 is going to be the trip to Channel 13 Weather Center. So if we need to finish that chapter first. So if we finish the chapter on Tuesday, it's conceivable we'll be going to Channel 13 either on Thursday or the next Tuesday. I'll have to try to arrange that.
Don't forget roll call.
Yeah, okay, I need to do that. Thank you. I need to also manage. All the king's horses. All right. Page numbers, first column. Everybody got that?
Yeah.
Second column, features with close lines.
And then
What does that mean? Indicate. What does that indicate?
widespread line.
And then features with widespread lines. And what does that indicate? Okay. All right. You don't have to write it as poorly as I did. You know, that's my prerogative. Okay. Do you think there's going to be? Yes.
I can't get the website on here to pull up.
Okay, that one may not. So I'd say Google or search for it somehow. But be sure you get the name of it right and see if you can get a topographic map or a leaf map of one and two. Okay. You think there's going to be more questions, or should I start uploading this? Well, let me go on. Yeah, I don't need to call the roll on it. So I think I'll upload.